This figure shows the block diagram of design in Vivado. Let's have a look at the different section of design. Clock generation. The IDT clock generator is responsible for providing the main clock signals that drive the system. It has differential clock outputs, labeled P and N. These signals are fed into the clocking wizard. Clocking wizard. The clocking wizard is a block that takes the clock input from the IDT clock generator and generates two output clock frequencies, 100 MHz and 200 MHz. These are used by other components in the design. Address generation. Two 10-bit counters are used to generate addresses for the block memory module. One counter is clocked by the 100 MHz clock. The other counter is clocked by the 200 MHz clock. These counters generate sequential addresses for port A and port B of the block memory. The addresses are 10 bits wide, meaning they can address up to 1024 memory locations. Block memory. The block memory module has two independent ports, port A and port B, both of which can be accessed simultaneously. Port A receives the 10-bit address from the 100 MHz counter. Uses the 100 MHz clock to read data from this address. Port B receives the 10-bit address from the 200 MHz counter. Uses the 200 MHz clock for data operations. The block memory acts as a lookup table where the sine wave data is stored. Based on the incoming addresses, the corresponding data is retrieved from memory and sent to other parts of the design. Integrated Logic Analyzer, ILA. The Integrated Logic Analyzer is used for monitoring and debugging signals inside the FPGA. In this diagram, Probe 1 and Probe 2 are connected to outputs of port A of the block memory, address and data. Probe 3 and Probe 4 are connected to outputs of port B of the block memory. The ILA module is clocked by the 200 MHz clock to ensure that it captures data synchronously with the faster clock domain. Let's begin the Vivado design. Start by creating a new project for the ZCU 104 board, and then add a block design. Within the block design, use the Add IP feature to insert a block memory generator. To configure the block memory, double-click on the IP. In the Basic tab, you'll find two controller operation modes for the block memory. For this tutorial, we will be directly accessing and reading back buffered data from the block memory. Therefore, select the native interface, standalone mode option. For the memory type, this tutorial uses block RAM as a lookup table to store pre-calculated sine wave values. These values are then read from the block RAM to generate the sine wave. Additionally, we aim to explore how to operate two independent ports with different frequencies. To achieve this, we will use dual-port read-only memory. Next, we open the Port A and Port B options tabs to configure the appropriate bit width and depth for storing the sine wave coefficients. We choose 11 bits for each port. The reason is that we are generating sine wave coefficients with 10-bit resolution for amplitude and an additional sine bit for positive and negative values. Therefore, the total bit width required to store each sine sample is 11 bits, 10 bits for magnitude plus 1 bit for sine. Additionally, we want both ports to remain continuously active, so we set the Enable port type to Always Enabled. This ensures that the ports are always ready for read and write operations without requiring external control signals to enable them. We deselect the primitive output register option. This reduces the block RAM latency to 1 clock cycle, simplifying the design and making the result easier to understand by minimizing delays. Open Other Options tab to load a memory initialization coefficient file. This coefficient file is used to preload RAM in an FPGA design with specific initial data. When the design is synthesized and implemented, the block RAM will contain the values provided in the file. Now press the Browse button and load the COE file. You can validate and then save it. Add programmable differential clock. From the Board tab list, add a programmable differential clock. This will add a clock wizard with a differential input and connect it to the appropriate external pins. Add reset. From the board tab list, add a reset and connect it to the reset pin of the clocking wizard. Note that when using the board examples, the board file's presetups are automatically used. For example, based on the board presetups, the differential input is connected to I/O pins AH17 and AH18, which are connected to the 300 MHz clock, and the reset input is connected to the M11 I/O pin, which is the CPU reset push button. Configure the clocking wizard. Double-click on the clocking wizard to open it. Set output frequencies. Go to the Output tab and add two frequencies with values of 100 MHz and 200 MHz. Allow the clocking wizard to add the buffers for routing the clocks into the clock network. Binary counters. Add two binary counters to the design and set the output bit width of each one to 10. Connections. Connect the clock pin of port A to the 100 MHz clock generator and link the output of the first binary counter to the address port for port A. Repeat this process for port B, connecting it to the second binary counter and the 200 MHz clock generator. This configuration ensures that port A operates with a 100 MHz clock while port B runs at 200 MHz. Integrated Logic Analyzer. Add an ILA to the design to monitor the signals at the output of the block memory generator. Double-click on the ILA IP and set the number of ports to 4 and increase sample data depth to 4096. It allows us to capture 4 cycles of fastest sine wave. The ILA is clocked by the 200 MHz clock, which is the faster of the two clock frequencies used in the design. The ILA needs to capture and observe signals in the system. In this design, since some signals are operating at 200 MHz, the ILA needs to sample these signals at the same or higher clock rate to accurately capture all transitions. Connecting the ILA to the 200 MHz clock ensures that it can reliably capture both the slower 100 MHz signals and the faster 200 MHz signals. Connect the address and data out of port A to probe 0 and 1 respectively. Repeat the same connection for address and data out of port B. Create top HDL wrapper and let the Vivado to manage and auto-handle it. Let's generate the bitstream and wait until Vivado finishes writing bitstream. Now let's download the bitstream into the device over the USB JTAG. Open the Hardware Manager and program the device with generated bitstream and debug probe files. After that, the ILA dashboard will pop up. To program the device, you will need to upload 2 files, bitstream and ILA configuration file. Usually, these files are located in the same directory, so as soon as you choose the bitstream, the ILA file with the similar name will be selected. You can press Run Trigger Immediate. It will capture 4096 samples and display them. Right-click on the 2 captured signals to change their settings. Set the radix to sine decimal and the waveform style to analog. After these adjustments, you will observe 2 sine waves fluctuating at different frequencies. After doing this, you will observe that the address and output data for one port update twice as fast as the other port. Additionally, you'll notice that the data updates with one delay following the address change. To observe the sine wave starting from the first sample stored in the block memory, we need the ILA to begin capturing data precisely when the binary counter is equal to 0. To achieve this, in the Trigger tab, click Add Probe and select the probes connected to the binary counters. Set the trigger condition to activate when the binary counters are equal to 0. Next, navigate to the ILA Settings tab and set the trigger position window value to 0. Finally, click Run Trigger. At this point, the ILA will capture data starting when the counter is 0, and you should see the sine wave displayed correctly, beginning from its first sample. Let's take a closer look at the binary output counters and how their output can be interpreted as analog signals. Make the captured output of binary counter as analog. This ties into the core concept of a numerically controlled oscillator, NCO. The counter in your design acts as a phase accumulator. As it increments, it effectively creates a digital ramp signal. This ramp signal represents a linearly increasing phase value, which is crucial in generating periodic waveforms, like sine waves when passed through a lookup table. This ramp signal, when plotted, would visually resemble a sawtooth waveform, illustrating how the counter progresses through discrete values. In our design, we use two different clock sources to generate ramp and sine functions with distinct frequencies. Although the current counter increments by a fixed step size of 1, you can introduce flexibility by modifying the step size. This approach would allow the phase accumulator to skip values, thus adjusting the frequency of the output wave. In upcoming training sessions, we will introduce an enhanced phase accumulator and explore how an NCO can generate sine waves with variable frequencies.